Hey guys, it's me again. Hope you guys have been hanging in there. I know it's been hard for a lot of us, even for myself, adjusting, but you guys have been doing an awesome job. I also have been grading the stoichiometric tests, and I'm still grading them, which is why you don't see the grades just yet. But they're turning out fantastic, and so I'm really proud of you guys. I know that we're going to be able to pull through this and get through all of this together. So it is Friday. We are going to end, I guess, this week. Having started a new unit, the solutions unit. Today's objective. Today we will apply the general rules regarding solubility so that we can investigate aqueous solutions. A lot of these key ideas you should have already been introduced to if you have been keeping up with the assignments. You should see a lot of these words becoming more familiar. So I'm just gonna kind of expand on some of these ideas a little bit today, and hopefully we'll get all the way to the solubility curve. We'll see how far we get. As I'm going through this and you're following along, what's great about it is that you can always stop and go back and rewind or fast forward, and touch base on focus on whatever you think you might need a little bit more help with. So please do that. Also, make sure you're taking notes. Remember, you can use notes on your quizzes and things like that, on your assignments. It will be really difficult later on to kind of be toggling back between assignments that we've already had where all the notes are if you're not writing them down. Continue to maintain a notebook so that you have a collection all right there in front of you as you're going through these videos and taking these doing these Google assignments and so on. So you're just not having to go back and forth between too many windows. So let's begin. I'm just going to be highlighting the definitions on this slide that you should maybe focus on. I did attach this already to yesterday's assignment. Or yesterday's or the day before. It's all blending together. So you should have already seen these next few pages. Understanding that a solution is a type of homogeneous, and we talked about homogeneous a long time ago, with homogeneous is a type of mixture that is made up of two or more substances. The difference between homogeneous and heterogeneous, remember, is how all of the particles are distributed. So in a homogeneous mixture, something, for example, like a Coke, if I take a soda and I open up a can and I pour a cup for you and I pour a cup for myself, because everything is evenly distributed, because it's a solution, our sodas are going to taste exactly the same. So that's essentially what we're talking about, and it doesn't necessarily have to be liquid to be defined as a solution. It's more of the fact that it's a mixture of things that are equal kind of all throughout, for the most part. All right, next definition that you need to know off this slide is definitely this solute here. Solute. That's what's being dissolved. That's typically the solid. If, for example, if I was making sweet tea and I poured a sugar packet into my tea, then the sugar would be the solute that is being dissolved. The solvent would be the liquid part of the tea, the water mostly. So the next word definitely you need to know is understanding solvent is what is supposed to be doing the dissolving. There are some guidelines in being able to determine if something would dissolve, or I say guidelines, but it's more like rules to determine, okay, if I pour this substance into this liquid, will it dissolve? will we see solubility occur? And that's not always going to happen. There are some substances, if we mix them together, they will not mix. And a good example of that is oil and water. If I put oil and water and in whichever order, they're going to separate themselves because water, as we've learned, is polar, and oils typically are non-polar. And when I go into more about the rules of solubility, we'll go more into depth in about this. But if I have a polar solvent, a polar solvent can only dissolve a polar solute. A nonpolar solvent can only dissolve a nonpolar solute. And so it has to be of the same polarity in order for solubility to occur, is one of the rules. And then there's more details to it. So again, I went into that way much more than what I wanted to. But that is kind of a preview of what we're going to be talking about next week. Gaseous solutions, as you see here, you can have a gaseous solution and you can have liquid solutions. In the solubility curve, we're mostly talking about a solute in a solution, especially in the solubility curve, particularly water. And so we'll go to the next slide. All right, there was some videos that I sent you going in detailing, explaining how water works, how it uses its polarity to separate substances. And so again, has to do with polarity and being able to pull apart. It does a very good job pulling apart ionic compounds, because ionic compounds tend to have a positive cation and a negative anion, and so the different poles of the different sides of the water are able to work into separating those molecules. The main definitions that I want to focus on this slide include electrolyte and non-electrolyte. When a water works to dissolve ionic compounds, we now have floating charged particles. And electrolytes are essential. Those charged particles are able to transfer chemical signals through in the form of electrons. It's how our body is able to deliver messages from our different organs, from our hormones throughout our body, going wherever it needs to go. That's why when you get sick, it's most important that your body is able to carry those communications through electrolytes, or in an electrolytic situation, I guess you could say, so that your body is able to heal and do whatever it needs to do. That's why we drink Gatorade when you get sick, especially if you have a lot of, not to be gross here, but vomiting. So electrolytes are essential for conducting electricity by being able to transfer electrons. A non-electrolytic solution is a solution that does not have charged particles floating around. And the water, sugar water is a good example of a non-electrolyte. The sugar separates, but sugar is a compound that has, or a molecule, I should say, that has carbon in it, and there are no charged particles. It stays together. That carbon is strong enough to hang on to all of its other elements. And so while water can dissolve things like sugar, it doesn't separate them to the point where they have these charges. And there's no charge, so if there's no charge, no electrons can be easily transferred through that solution, so electricity cannot be conducted in those solutions. Electrolytes and non-electrolytes each have their purposes. we'll go into next week more about what a strong electrolyte and a weak electrolyte is. And I already did that. I think I did ask you some questions because one of the videos I posted did go into that. But this will be coming up a little bit more. Strong electrolytes completely separate from each other, and in this example here, we have these completely being separated. The positives are completely separating from these anions here. So this would be, from the picture that I see, this would form a strong electrolytic solution. But if I only had partial dissociation, then that would be considered a weak electrolytic solution. Like I said, we'll go into more details next week about that. All right, so there's a lot on this page, and half of it we don't even need to go into. The main things we need to kind of focus on here are these definitions of saturation. So saturated, unsaturated, and supersaturated are definitely terms you need to know. A saturated solution is when you have basically just the right amount of solute to solvent. Everything's kind of evenly distributed. Obviously, it's a solution, but what I mean to say is there's just the right amount of solvent to solute in order for all of it to dissolve. Sometimes you hit a saturated solution, you have just a little bit of solute on the bottom, but not a whole lot. But just a little bit is one way that a chemist would know that they've reached the maximum amount of solubility for that solution. When I keep saying the right amount, it doesn't necessarily mean equal amounts. I could take 100 grams of water and 100 grams of sugar and have an unsaturated solution because there's way more solvent to solute. So I'm not talking about equal amounts, but rather just understand that it's just the right amount of solute to solvent that everything gets dissolved. An unsaturated solution is when you have a solution where you have, in simple terms, way more solvent than solute. So you have a lot, I don't know, I can't make it any more simple. Basically, solute is, let me see if I can, solvent, oh man, sorry. Let's try this again. Okay, let me change my pen here. All right. Okay, I think I got this. Nope, I don't. And my point is huge. Okay, let's go here with this one. Let's try this one. Okay, let's try again. In an unsaturated solution, my solvent, oh, this is fun. Oh boy. Is greater than my solute. I ran out of room. You get the idea. That's really all you need to understand about unsaturated. Supersaturated is when it's opposite. You have way more solute than solvent. There isn't enough solvent to dissolve all the solute. So you tend to have a lot of solute sitting on the bottom of that solution. So here, solvent, excuse me, is less than the solute. If you can understand that, that's basically all there is to understand. All right, so there are some factors that affect solubility, and we'll go into the rules of solubility and rates of solubility next week. But as I kind of already went over a couple of slides ago, knowing whether something will dissolve or not depends on if they are similar in polarity. So polar solvents will dissolve polar solutes, and nonpolar solvents will dissolve nonpolar solutes. So that's just a general rule, very, very general rule that we use to determine if something would dissolve in a solvent. The main thing I want to focus on here is the solubility graph. And there's a lot of lines and there's a lot going on, but let's just kind of break this down a little bit. Chemists use solubility charts to help them analyze, in their experimental designs, to analyze, certain, one example might be if they find chemicals in a river and they're doing an analysis of different chemicals that are found in that particular body of water. They'll use a solubility chart to make certain determinations and assumptions about what that system is like, what that ecosystem is like. And so there are lots of real world applications to solubility charts. So let's break this down a little bit and what this graph is telling us. First of all, along the y-axis, we see that this is the grams of solute per 100 grams of water. So we're only looking at all of these substances being dissolved in water. And then we see along the x-axis temperature. And as we move across that, as we move across the the x-axis, we see that temperature is increasing. And as we go up the y-axis, we see grams are increasing. This is grams of solute. Remember, grams of solute, not the water, not the solvent, the grams of the solute. Each one of these lines is representing a different substance. So this is the solubility curve for potassium iodide. Here we have the curve of solubility that goes through here, representing sodium nitrate. Here, this line down here goes up pretty steeply. That's representing potassium nitrate. And so as soon as you can start breaking down and seeing that there are all these different lines that are representing different types of solutes, then we can step back and we can start kind of seeing some trends. First of all, the other thing I want to point out in this graph is that the solid lines are representing gases. I lied. The dotted lines are representing gases. The solid lines are representing solids. So here we have a solid. Here we have a solid. Here we have this line that's representing a gas. This line down here is representing a gas. So here's a big takeaway from identifying gases from solids. We see that with a solid, we have a direct relationship with temperature. So solids have a direct relationship with temperature. I should try that. Let me try this again. Let me start over with this. I know you can't see what I just did, but solubility for solids, if solubility increases, oh my goodness, sorry guys, it's because temperature is increasing. We call that a direct relationship. Solubility for solids increases as temperature increases. That's not the same situation for gases. But hold on, we'll get there in just a second. Notice how all of the lines for solids, as temperature goes up, the line for solubility for a solid is increasing as temperature increases. For gases, though, we see that as temperature increases, solubility is going down, and there are several reasons for this. Gases are already far away from each other. They're in a state where the molecules are far away. They have very high kinetic energy. And anytime you increase the temperature of a gas they're already far apart from each other. But if you start increasing that temperature on them, they move even further apart from each other. And so then that makes trying to dissolve that particular gas in water more difficult because there's just not as many molecules around. And so for gases, solubility, I'm just going to abbreviate here, decreases as temperature increases. That's the rule for gases. And we call that an indirect or an inverse relationship, where solubility goes down, temperature is going up. And it's just an inverse or an indirect relationship is when one goes up, the other goes down. Whereas, again, remember, solids have a direct relationship. Solubility is increasing as temperature is increasing. One goes up, the other is going to go up. If I start to decrease the temperature, well, what's going to happen to solubility? It's going to decrease. And so we can take, for example, I could take, I could make a solution of sugar in water, and I could pour a whole bunch of sugar in there, and solubility not be very good. I could have a supersaturated solution. But as I start to increase the temperature, then I can get more of my sugar to dissolve, increasing my solubility. And so now I can go from a supersaturated solution to a saturated solution, for example. But as soon as I go back and turn that stove off and I start cooling that solution down again, the sugar is going to go back to being a solid. I don't know if you've ever made, for example, like rock candy, or or you've ever tried to do grow any kind of crystals. You make a supersaturated solution at a very high temperature, you dissolve everything, and then you let the solution cool, and over time that solid goes back to being a solid, and you see these really amazing designs and really cool things. I'll have to find some pictures to share with you guys later. But let's continue here. So now that we've kind of tackled the general basics of solubility, let's start looking at the different parts of it, how to read it. So let's just kind of focus on, we'll work on this sodium nitrate right here. We see that sodium nitrate is a solid. It increases solubility as temperature increases. And if I start looking at the numbers of the graph, let's just do a point. Let's say I know you can hear me tapping on this while I'm trying to get my thing to work. Let's just say I have a point like right here. I have this point. And the question that you might see is, at 40 degrees Celsius, at 40 degrees right here, how many grams of sodium nitrate would make a saturated solution? Well, I'd go to the 40 degrees and I would go to where I hit my line, and on the line we see that approximately 100 grams of sodium nitrate would dissolve in 100 grams of water at 40 degrees. let's take it a step further. Let's say, okay, that would be called a saturated solution. But what if my point is up here? Okay, at this point, at 40 degrees, at 40 degrees Celsius, same temperature, I didn't change the temperature, but what I did do was I added more solute. I added more sodium nitrate. So now I have 130 grams, and we are way above where the line of saturation is. So what does that mean? Well, that means we would have what we call a supersaturated solution. Supersaturated. So if I'm way above my line of saturation, we now have supersaturated. Okay. Same idea, same point. I mean, same solute, but let's say we have only 80 grams. Let's say we have only 80 grams of sodium nitrate at 40 degrees Celsius. Well, at 40 degrees Celsius, 80 grams, we would have what we call an unsaturated solution. So these points, so the line itself is showing us along the line how much exactly solute I can add to make a saturated solution. So along the line tells me what a saturated solution would have. If my point is above the line, I now have a supersaturated solution. That means I have way more solute than solvent. There's not enough solvent to dissolve all of it. And if I have a point that is below this line of saturation, I have what we call an unsaturated solution, where I have way more solvent than solute. And basically that's how we read this graph. I know you're kind of like, wait, what? And again, there's a lot to read on this graph, but we're going to be spending the next few classes just working on how to read this graph, and just kind of showing you all the different things that we can do with this graph. Before I leave this slide, I want to review a few things that we cover, because it was a lot. First thing, remember to generally just very basically determine solubility. We determine, okay, if I have a polar solvent, I need a polar solute in order for it to dissolve. In order for a non-polar solute to dissolve, I need a non-polar solvent. Then getting to the solubility chart. Let's review this real quick. First of all, along the y-axis, we see temperatures increasing as we move across, and that along the y-axis, we're looking at grams of solute. We said that solids have a direct relationship with temperature. So as I move across the graph with this sodium nitrate, for example, and temperature is increasing, my solubility for the solute is increasing. So I can have way more solute dissolve because solubility is increasing. Also remember that along the line is the line of saturation. So at any point, if I said, okay, I'm at 10 degrees Celsius, my saturation point, or the amount of solute that I can have to dissolve in water for sodium nitrate, is probably 78 grams of sodium nitrate. If I'm all the way over here and my temperature is all the way at 80 degrees Celsius, then the amount of solute I can dissolve to make a saturated solution is about 145 grams. So all along the line is what would make a saturated solution. A point above the line is a supersaturated solution. A point below the line is unsaturated. a point on the line is saturated. Also, one more trend to go over. Again, I'm sorry, I know this is a lot, guys. Relax, it's okay. Gases, when temperature increases, solubility for a gas decreases. And the reason is because the gas molecules are already far apart. As temperature increases, they move even further apart from each other. And so that makes trying to dissolve that gas into water much more difficult. All right, guys, I'm going to kind of stop right here. That was quite a bit. We haven't practiced this, and I just don't want to overwhelm you all at once. We have the whole weekend, so you have today and you have the weekend. I'm not going to give you an assignment along with this at this point. I guess your assignment is to take notes. So this is my suggestion, is that you go through this, and then go back, maybe Sunday or something. But because of the length of the notes that I'm expecting you to take on this, I'm not assigning anything that you need to turn in over the weekend or anything like that. On Monday, we'll pick right back up where we left off here, and I'll do more practice problems with you, and we'll look at, we'll do a quick review, mostly focusing on solubility chart, and just so we can get that practice in and everything. Again, I think you guys have been awesome. You've been super troopers, especially all those of you who have been checking Google Classroom every day, responding, letting me know what you're having trouble with. I thank you so much, and I'm thinking and praying for you and your families, and hope that you guys are okay. I'm hoping that soon we'll be able to do some sort of Hangouts or Zoom or some sort of virtual meeting. I'd like to see your faces again. So don't stress too much at this point. If you're running into any issues, remember, just send me an email. I'm checking my email all throughout the day and trying to respond to everybody. And we'll pick up on Monday. I'll see you guys soon. Take care.